can get by with it. Oh, that was a little bit quick. So this is just a quick example of a CNC machine. This is a Haas machine, very similar to the ones that I learned on. It's a 5-axis machine. You see over on the far right there, your workpiece gets bolted down to this. And we would start out with just a blank billet of steel. This is your subtractive process. It can move in all 6 axes. So the part moves in 2 axes, and the cutter actually moves in 3. So you can get some really ridiculous part geometries out of this, out of a single machine. So you're not locked down to just drilling a straight hole or just doing rectilinear moves. This can do complex organic shapes. So again, if we want to reproduce that robotic arm and we need some funny curves in it, we can easily machine it just as well as we can cast it on block. We've got other removal techniques that were probably going to be really, really common. Sawing imparts tool wear. So we've got a saw blade that actually has to cut stuff, just like the CNC mills. Any rotating part that's going to be moving past a piece of metal is going to wear out. But we can get around that by not actually having a blade whatsoever. We apply that same CNC technology to a plasma cutter. This is a handheld torched over on the right. It's really, really cool. You apply a high voltage to break down an inert gas or just air, and then apply a huge amount of current, and you can cut through metal with it. You just get a stream of plasma. It's about as close as you can get to a lightsaber in real life. Strap one of these to a CNC machine, and we can cut round stuff, flat stuff, you name it. You can cut stuff inches thick with enough current. And this is electricity, so we're not consuming something like acetylene or methane or something that we'd have to ship in. We just add more solar panels or maybe drop a nuclear reactor. If we've got the electricity, we can burn it in, literally, in metal. Again, with the CNC stuff, there's a key difference between a CNC mill and a CNC router, even though they kind of look the same. Routers, like this little shop bot, that are ubiquitous in maker spaces for cutting wood, plastic, and aluminum, tend to be shorter and longer or wider. So if we're going to be cutting sheet metal parts or large flat stock, you'd use something like this, but they're also a little bit less accurate. For large items, you just kind of run into this rigidity issue. On the moon, I'm not actually sure how that's going to work because gravity's lower, but inertia stays the same. And a lot of the rigidity issues that you work with CNC machines are the inertia of the cutter or the spindle just kind of wanting to keep going according to Newton, and you're having to stop it rapidly, which shakes the entire machine. So scaling things up for truly large structures may be easy because we can move stuff around easier, but we may wind up slowing things down by the same token. And then on the left here, again, going huge. The shop bot on the right would fit on this desk. This is my buddy's CNC that we've been building in his garage for the past few weeks. And it's 52 by 56 inches. And I think the total cost to build it is somewhere in the neighborhood of $300 to $500 right now. By the time we turn it on, it shouldn't be over $500. This is what we can do on the moon if we've got some local resources. 90% of the mass of this is produced from flat steel stock that we cut apart with a plasma cutter, and he's just cleaning up an edge there with an angle grinder. This is something we could build on the moon as soon as we have the ability to produce standard stock sizes. At the other end of the spectrum, we've got additive manufacturing. Powder bed printers are probably going to be the way to go since we're starting out with really small particle sizes already. The lowest energy approach would be to stick with small particle sizes. If we have a stream, however, of really hot molten metal, the lowest energy approach would be to keep it hot and use something like a rolling mill. If you're looking for a quick primer in how a continuous casting machine works, I normally tell my students to stay as far away from Wikipedia as possible, but in this case, the article is actually really good. Just don't tell them that. So over on the far right is actually the image from that article, and I didn't include all the numbers because I knew I'd be running out of time probably. But up at the top, you've basically got a bucket of molten metal. We call that a crucible or a ladle. And this goes into sort of a primary vessel that gives you a little bit of buffer on the flow rate where it starts to cool the metal down. It then goes down into these molds, and it's coming out sort of molten, but it looks about like toothpaste. It's coming out really slow, going through this mold and then getting rolled out to the dimension you want. So you go directly from liquid molten metal to a solid piece of bar stock. And that's kind of important. If I can have that piece of, right on the top there, just pull it right out. here on Earth, if we want to build virtually anything, we start out with standard stock sizes. This is just an I-beam. It's an aluminum extrusion. I apologize for having brought aluminum examples while I'm talking about steel, but it's what I'm actually working with right now. I've got some ingots and a sample casting down there as well. But this is what makes our economy tick. I can call up Frank down the street and get 20-foot sticks of this stuff within an hour. If I call up the best metal supplier on the moon right now, I'm going to be on hold for a really long time, and believe me, they're getting a bad Yelp review. But it doesn't have to be that way. This machine can be stupid big. It can handle hundreds of tons of steel at a time, or it can be scaled down to handle a ton or two. The advantage with going big is sort of energy. You might think, all right, we're going to burn a lot more energy, we need to scale up, but the efficiency goes up just because of surface area to volume ratios. The larger the piece of steel is that I'm working, the longer it stays hot. Now, in the vacuum on the moon, that may not actually be such a critical factor simply because vacuum is highly insulating. When I'm standing over a really hot piece of metal, I'm getting a blast of hot air in the face all the time. Gotcha. Because of convection. So that benefit is not something that I'm able to calculate simply because I don't have a really large vacuum chamber. If you got one, I'd be happy to forge a knife in it. Just give me a pressure suit. So anyhow, at the end of this process, we can have literally any shape we want. Tubes are a little bit weird. You have to punch a hole down the center and then run them through this process. But it's still a single forging operation. One machine, the same machine with a couple of attachments can do virtually any shape and size you want. Hexagonal, square, rectangular, even sheet metal. And the real advantage of being in a vacuum is this. You see on the sides of the bars there, you've got this sort of mottled texture. That's the fire scale because this is being done in an oxygen atmosphere, Earth. On the moon, that wouldn't happen. It would just be a really, it would look like a lightsaber going through there. It would just be perfectly clean. And at the end of it, you'd have a piece of material that looked cold rolled, nice clean surface that never had to be descaled. So we're saving energy and time and not having to process that into a clean piece of material before we put it to our manufacturing process. Here's the other cool part. We don't have to worry about the size of our roads on the moon. So if we're producing this, down the street, we can have a 100-foot bar and just bring it right over to our manufacturing facility. Whereas if I wanted a 100-foot long anything here, I'd have to shut down the interstate just to move it, a couple of miles. It brings up some interesting implications for the size and kinds of things that we can do in space versus here. And so this is sort of my wrap up, and I'm going to open up for questions as quick as possible. Again, there's no single magic bullet. 3D printing is not going to save us, but it's going to be really important. Telerobotics will not save us, but it's going to be really important. The rolling mills are already done with telerobotics, even though the guy's only like 100 feet away. But that steel's really hot, and I don't want to touch it. Certainly not when it's 100 feet long. So it can augment our experience on the moon and our productivity, but the concept of a true lights out fab where you just sort of turn the key and then come back 6 months later and there's 40 tons of material there just isn't really going to happen in the foreseeable future until we have like general purpose AI that can do there's a burr here that's jammed up the machine and keep it going like a human can. Selective automation, however, can leverage our timetable. If we can multiply that force of one person operating many CNC machines to produce thousands of parts per day or week, then we can get a lot more people sustainably supported on the surface a lot sooner than if it was just done with sort of this manual labor approach, one person, one tool, one job. And that's sort of how I built my career. If y'all have questions, I'm going to grab my props and we can answer them. What you got?
Can you talk to changes in joining technologies based on operating A in vacuum and B?
I did totally skip over welding. Fasteners are going to stay the same. But as far as TIG welding or MIG, all of our welding processes are basically the same idea. You're passing an electric current, well, unless you're using gas, which we're just not going to use up there probably. You're passing an electric current through to the base metal, melting both base metals and adding some filler rod. MIG uses the filler rod itself as the feed. All of these processes would be benefited by vacuum, but I'm not sure if we would need the shielding gas simply to conduct that arc. But I think we'd need a lot less of it. So.
From a shielding and corrosion.
Yeah. Like, we don't care about oxidation. It's just not going to happen. But we need something to conduct that. And we could use something else, probably.
Spray metal transfer probably.
Probably. Because, everything's going to wind up freezing out and not sticking. And, yeah. What you got?
Yeah, since you mentioned labor at the end, I'm curious, operate these things. This big plant that you're talking
Yeah.
about, a guy taking a burr off of it. So there's still definitely jobs that people are going to have to do.
Oh, sure, absolutely, yeah.
Assuming there's no general purpose AI.
Yeah, right. Certainly not that we fuse with. So that, a mini mill that runs 100 tons, I think there were 20 employees working, full time. And there's literally like 6 guys sitting in a booth that are doing most of the work, twiddling the knobs and stuff. Just about everybody else starts the process, and then you're standing back waiting for something to screw up. And you might go, hours to days without that.
So you could be a machinist while everything's.
Oh, sure, yeah. That's what I'm saying. Humans are not specialists. Insects do that. So we can do lots of jobs. I mean, Jesus, I do. I'm a biologist and I cast metal. Just as a quick example, this is an actual failed casting. A couple of the parts came out okay, but none of the good parts do I have because I had to ship them out. But these are motor mounts for a UAV, and it only failed because I got impatient and quenched it too early. But basically, you have this is an investment cast. So we 3D printed the parts, stuck them to a sprue, put them in some plaster, burned out all the plastic, and then poured our aluminum in. And we can send this around if you're just interested in seeing what a cast aluminum part looks like. Done by a biologist. And this is a CNC machined wheel hub. And then these are the ingots that I use to get to there. So I take scrap and I can clean it up. It's a lot cheaper for me to get good quality scrap than it is to buy ingots, especially when I'm doing small runs like that. What you got?
You have an online site?
Wetspark.net. That's our website.
Wetspark?
Wetspark.
Oh, Wetspark.
Yeah. So it's sort of a play on the biology and the blacksmithing.
Okay.
This is just a wheel adapter. If you've never seen a CNC machine part before, there's a little bit of sawdust on it. Sorry. But this is a machine part. It was milled. It's just a wheel hub adapter. Y'all are interested in seeing that. And if you've never held a cast aluminum billet, there you go.
Hey, Ryan.
Yes.
What about teleoperations, telerobotics? It
Oh
seems like-
yeah, so automation is one thing, telerobotics is another, but again, there's some things where you didn't design the robot for that, and that's the one thing holding you up. So if I've got telerobotics to do all the sort of heavy lifting, that's gonna help multiply that force again. And we can get things set up initially so that it's safe to land, but then I think a skeleton crew of at least like 5 to 20 people to set up this sort of tooling would be really advisable. Just to make that sort of on-site decision you can't get through a camera.
I assume on Earth, when you're using, making steel and stuff, there's a certain cooling process that oxygen or air has an effect on. What about on the
Yeah, I absolutely hate it because I would really love to keep eating the metal instead of having to keep sticking it in the fire. The insulating nature of vacuum is great because it will keep the heat in the part. But also it's not forming the oxide. So if I'm making a knife or something that has to be really pretty, you're going to get dings in the surface because you've got this layer of oxide that's really hard and insoluble. And when you smack with a hammer, you're driving it into the surface. And so you get these pot marks that just looks nasty. Like I was saying with the rolling mill, that scale on the side, I get the same stuff when I'm doing small stuff. But if that never forms, then I've got this clean virgin surface that should be shiny when it cools.
What's the difference in time?
Oh, it'll take longer to cool down.
Okay.
Yeah. You don't have convection
Like
current. It just takes a lot longer.
or-
Yeah, I mean, how long does it take your coffee cup to cool off versus when it's in a thermos? Same exact difference. I mean, even better.
Okay.
Yeah, like hours versus minutes.
Okay, so you're on the moon, gravity is good, I get it. If we wanted to do a lot of this stuff in zero G, would you spin it? I mean, is it a completely different technology?
Yeah, there's no real easy way to reduce gravity. I can make it bigger by spinning it, in a centrifuge. But to get zero G, we're gonna have to go into orbit, which on the moon is really easy.
Can you do this in zero G?
Oh,
Or do we need a completely different level
Like
of
how is the
technology?
moon's gravity get?
Yeah, so the moon's gravity, yeah, that's the one thing I didn't touch on with that rolling mill. So you've got this massive chunk of, or pot of molten steel that you're trying to allow drain. The gravity's lower, so it's gonna move slower, but it's also staying hotter longer. I don't know if those balance out. At the very least, you need to make the tower a little bit taller to let it get to the right temperature before you start rolling it. And that's fairly simple to do. I mean, we've got enough steel where we can make a dumb structure just a little bit taller. But as far as like zero G, that would be a little bit weird. You have to pressure feed stuff. And there's definitely materials that can stand up to the temperatures. It's just a matter of you have to force that material through. Another interesting thing about metal, since it's conductive, you can run a small electrical current through it and use a magnet to force it, like Hall effect, basically. What's up?
Yeah, have you given any thought as to which kinds of processes might be better in zero microgravity versus 1/6G?
Yeah, so like I would never try to forge a knife by hand in zero gravity. I would probably never put a power hammer, on the space station. Everyone would hate me. But a hydraulic press, sure, it's a totally symmetric process. So you're not slinging stuff around. Oh, that's the other thing. So gravity's lower, but if that robotic arm picks up something that's 6 times heavier than it's supposed to, it won't break until you try and move it over there, and it just keeps going. Because the inertial loads are the same. Sorry guys. So you slow things down a lot.
Last question.
Sure.
That was the last one.
Oh, that was the last question.
Yeah. I
Oh, I'm
apologize.
sorry. Yeah, I'd stay here all day.
Ryan, come on back here. We forgot to do this, but let's go ahead and start checking off the different things that are needed to achieve Earth independence as we're addressing them. So actually, Phil, if you want to go ahead and check off, there's the oxygen.
Yeah, so when you make metal, you're going to get a lot of oxygen. In fact, this is what I worry about the most, is what to do with all the oxygen.
Yeah.
Because by definition, you're making oxygen that doesn't have a fuel to go with it. So what do you do with all that oxygen? But the other thing is we're going to make water.
Plenty of
We
water.
talked about the water on the moon. To make it drinkable, you have to have filtration or cleanup, but that's available, or it's in work. And then I'm going to put a dot in equipment reproduction because we can make metals to go into that equipment.
Yeah, thank you. And then, Ryan, I think you got you
Okay.
can complete that dot.
Yeah, I think so. Yeah, we can make stuff now. Interesting temperature control. So I don't think I actually mentioned it, but we might need dumb structures to cover up some of these items that can operate in vacuum to keep dust and stuff out, but also to protect the machinery that's not supposed to get hot from just direct blast solar radiation all day long. So it's really just a shade structure, a place to sort of kick the dust off of your proverbial boots, even if it's just a machine doing that. So I don't know, do we want to address temperature control or?
No, under habitats.
All right, that's under
Yeah.
habitat. All right, cool.
So, thank you.
Cool, I think you got it.
Okay, I'd like to invite Antonio and the students to come up. We're going to have a student presentation. Do you have a PowerPoint? Okay, excellent. And this will be about 10 minutes.
Can I pull this out?
Sure. I have no idea whose it is.
Actually, that might be mine. I think that is mine. Looks like mine. Right. I just want to get the team over here up here. Right. Yeah, come up here. Right here. Right here. Okay. Good morning, everyone. I'm gonna get this a bit closer. Good morning, everyone. I am Antonio Stark. I'm the Vice Chief Coordinator for the Student Track here at ISDC 2019. It is my pleasure to introduce you Team Deimos from Romania, one of the winning teams at this year's NSS Space Settlement Contest. The competition is organized by the National Space Society and has inspired tens of thousands of students to develop space settlement concepts since it started back in 1995. We at NSS believe that expansion into outer space is of particular importance to mankind, and these students are the very architects and engineers who will build that future. Please give them your undivided attention for the next 10 minutes, and please feel free to follow up with them afterwards if you have any questions. Now I turn the microphone over to Team Deimos.
Good morning, ladies and gentlemen. We're Team Deimos from Tudor Vianu National High School of Computer Science, and we're going to present you our space settlement concept. To begin with, the location. Our space element will be placed around Deimos, a Martian moon. We chose this location, particular location, because Deimos might be a C or D type asteroid coming from the outer solar system, thus it might have brought water in here. The population will be of around 240,000 people aboard.
Next up, we have the external structure, which I will be talking about. First, the main components. We'll follow up with a short video here, with a quick view outside, if it starts working. It's not working here. Anyways, I will be explaining the structure of the base. We will have 4 main tori around the base. If you can just go to a previous picture here. We'll have these 2 Gemini tori where people will live and work. They are symmetrical and will house the population. Between them here is the docking torus, or otherwise known as a spaceport, where ships will land. And on the interior here, we'll have the agricultural torus, where a lot of our farming stations and wire generations, air supply, and energy productions will take place. Also, we'll have the spaceship built in low Earth orbit, starting from connectors that will connect the base, and will transport a lot of people and materials between them.
Regarding the materials used, we chose a 12-layer shielding. Many of the layers will contain titanium. We chose titanium because it can be extracted from Mars. As you can see, we have also at the bottom of the image, there are 3 alternating layers of Mylar and Captain. We chose them because they are great thermal insulators with a thin net between them. And the blue part is actually the current-carrying wires that will create a magnetic field.
Additionally, I'm going to speak about the life support. The oxygen will be produced by using photosynthesis and the electrolysis of water. Additionally, spiraling algae will be researched on board in order to supplement the supply of oxygen. Power will be produced throughout nuclear fission. Our reactor, which is presented in the photo, will be similar to the sodium-cooled fast reactor. Next up, there are the atmospheric conditions. Each torus will have its own ventilation shaft with purifiers. The temperature controlling system, the humidity regulators, and the sensors will be connected. There are some systems that we created at school, and some measurements we took to make sure that everything is all right. Water will be mainly recycled, but there will still be some loss, and we think a solution might be asteroid and comet mining. Lighting will be composed out of the micro lighting system and the macro lighting system. The macro lighting refers to the sky ceiling and the street lamps, while the micro lighting refers to all indoor lighting. The sky ceiling will simulate the day-night cycle.
Next, I'm going to talk about internal structure. And the highlight of this slide is the living quarters. They are inside the Gemini toroid, the 2 of them, between the city level and the space park. This is where all the people will live. We took the 240,000 people and divided them into ever smaller groups. And the smallest group we got to was 100 people group that will be housed inside of this 100 by 100 area. Which has 12 blocks in the middle, some elevators that connect all the levels of the Gemini toroid. Then there is the interior design. This is about the city level. We were supposed to have a virtual tour of the city that should have highlighted some of these sites, but I don't really think it's working. Then there was an attraction, the space park, which you can see. I'm sorry, I have to skip a couple of slides to give you a view of the space park. This is the space park. It's located on the outside of the base. It gives a view of the red planet and the outer universe for people to recreate. Then we're going to talk about the transportation.
I'll be talking about the transportation. First up, we have the intertoroid transportation. Just a second. Okay, the Gemini Tor will be connected by a 700-meter long passageway, which will be accessible by both bike and on foot. And the agricultural Taurus will be connected to the Gemini Tori by a series of funiculars, which will transport food and other resources for the people to use. As for long-distance transportation for the people, we will have a series of electromagnetic railways. We are running around the space station on the outside to negate the effect of air friction. These railway stations will be set 5 kilometers apart from each other, so no point on the base is more than 2.5 kilometers away from a railway station. Next, we have the spaceport, which will be responsible for housing our spaceships. It can accommodate up to 200 spacecraft, which can carry up to 20 people each. Every 6 months, these spaceships depart and arrive, meaning that 4,000 people can choose to either leave or join the space station at once. For Mars ascent and descent, we will use railgun technology to shoot landers towards the, it's funny, to shoot landers towards the Martian surface, which will supply our research outpost. And for people transportation, we'll use a small MDV, which is very poorly animated over there.
We'll have 3 main laboratories aboard. We will have the biochemistry laboratory. Its main purpose will be to study whether human could ever inhabit Mars, and thus here all the samples collected from our Martian base will be analyzed. Then up next we have the physics laboratory. It will be split into 2 departments. We have the Q lab, where we will study quanta, more specifically gravitons, because we want to see whether gravity is determined by gravitons described in Feynman's diagrams. Then we have the astrolab, where it will be a sort of control center for the telescopes. We will have 2 particular telescopes. Then we have the engineering laboratory, split as well into 2 departments, the AOG, aerial group operations, and the GOG, the ground group operations. As I mentioned earlier, we will have 2 telescopes. We will have the Hofstadter telescope, which will be an optical telescope. It will have 1 primary mirror and an ACC, advanced camera system. We will use it for close observations, such as the spectrum of stars or close celestial bodies observations. And it will have 2 antennas for accessibility for the self-sustainable network aboard Deimos, DeimoNet. Then we have the Feynman telescope. The Feynman telescope will be an infrared telescope. It will have 1 primary mirror, hexagonal shaped. It will be placed in Lagrange point 2 of Mars, and it will have its purpose to deep space observations, such as observing the supernovas. Regarding space mining, we will use geosats. They are small satellites that will extract minerals and rocks from the Martian soil or from the comets and asteroids, and we will also want to study the isotopes of water.
Next up is the network that I'll be talking about. Keeping it short, there will be just 2 networks. The DeimoNet, which is basically like the internet, but for the people on Deimos, and that will connect both Deimos and the Earth, and a smaller network for robots to ensure that everything is running within parameters. As you can see in this picture, these here are the alveoli, which will hold all the servers and the crew working aboard in IT.
Lastly, there's the social infrastructure. One of the things that we took into account when designing this base was its lifespan. Thank you. Thus, we decided to make it capable of housing up to 500,000 people. Then we have the jobs distribution in here. As you can see, the vast majority is dedicated to the industry department and then the research department. We'd like to thank NSS